the very beginnings, the very first sentence actually of our book in 1998 was 1986 was, why are people smarter than machines? And we argued at the time that the AI systems that were in use in the 70s and 80s were, they were very brittle rule following systems that couldn't really utilize context and exploit many simultaneous constraints to influence the outcomes of their processes and to integrate information from many different sources to make sort of intuitively plausible decisions and judgments in all kinds of different aspects of cognition and perception and memory. And so we argued for a different sort of model of intelligence. We proposed a set of ideas called parallel distributed processing, which was already mentioned, as an alternative to the way in which people were thinking about cognition at that time. So the basic ideas that we were using were actually the ones that I think are the core principles of AI systems today. We proposed that processing in our brains occurs through the propagation of graded or continuous activation signals among simple processing units. We propose that representations are distributed patterns of activation across these units, and that the knowledge in the system is in the connections that link the units to each other. And finally, that learning occurs through adjusting the connections, maybe to make the output of our network match a target, or to maximize reward, or to maximize some other objective. And at the time, these ideas generated a lot of interest, but they had a lot of limitations too, according to many people. And this led many to abandon them around the turn of the century. But about 10 years later, all of that began to change. And in some ways, today's AI systems are pretty smart. They function well enough to be used every day for speech recognition, language translation, and many other things. They exceed human performance in games like chess and Go, and they're getting more and more powerful every day. The large language models and visual language models have become ubiquitous tools, threatening to replace humans in many domains. In fact, back in November 30th, 2022, Sam Altman said these things just as ChatGPT was being released. He said, language interfaces are going to be a big deal, I think. Talk to the computer, voice or text, and get what you want for increasingly complex definitions of want. This is an early demo of what's possible. Still a lot of limitations, so very much a research release, but soon you'll be able to have helpful assistants that talk to you, answer questions, and give advice. Later, you can have something that goes off and does tasks for you. Eventually, you'll have something that goes off and discovers new knowledge for you. Pretty amazing, huh? So a major innovation in neural networks that made this possible was the core operation inside of the transformer architecture, which is at the heart of today's large language models. And I'm going to talk a little bit about this because I think it's actually an extremely powerful part of what makes today's AI systems as smart as they are. But I'm also, as we go along, going to mention a few limitations of this. So let's just walk through a simple example of how this attention system works. Let's suppose you hear a sentence like, upon hearing the doorbell, Amy's Labrador began to bark. I assume you all know a Labrador is a kind of a dog, a very large and vocal type dog. So upon reaching the word bark, the language model has reached a word that actually is ambiguous between the sound that a dog makes and the surface of a tree. And it resolves this ambiguity by issuing a query. And a query is a pattern of activation, which I've represented here as little vertical bars representing the degrees of activation over a very small set of neuron-like processing units or elements in a vector inside of a computer. And this query is compared to other vectors called keys associated with all of the words in the context. And I've just shown 3 of them here, but let's imagine that these 3 vectors here are the patterns for the key vectors for upon or a Labrador or doorbell. And so based on the goodness of match or the dot product between the query and the key, then the keys, we get a high attention score for Labrador. Labrador matches this query and sends back some value vector. And the value vectors are, of all the items in the context, are weighted by their attention scores and added together. And so we get this composite value vector, which is largely determined by the Labrador. And this can tell the model, oh, gee, there's something in the context that's able to produce a barking noise. Maybe that's telling me how to interpret this word, but also it probably tells you that this is going to be a very loud barking noise. And indeed, when this sentence like this was presented to GPT-4 a few months ago, the model followed this with the word loudly. So the model uses context to obtain information both about the meaning of the current word, but also about what should follow that word. And just to make sure we're all on the same page about how this works, as each word is being processed, let's say here at the end we have the word bark coming in, this query is generated and compared to the keys of all the previous words across a context window that can be thousands or even millions of words or tokens long, and a composite retrieved value vector is brought back as a result of this from all the preceding elements of the context to influence the processing of this item. And we can think of this, and for the case of the word bark, as taking an input vector here, which is initially but somewhere a mixture of, I guess, the vector for making a barking sound or being the skin covering a tree, and moves it in the direction of being a barking sound, and also informs the model that the word is going to be loudly. And this is structured across many, many layers of this computation. So here I'm showing a slightly different example where we have a slightly different ambiguous word, in this case, bat. But as the model processes this word and here, it's using this process to gather information from the context and produce the next output, which in this case should probably be RAM, since when someone hits a ball with the bat, they're probably going to run to the next wicket or first base, as the case may be. So this innovation is in some ways incredibly satisfying from the point of view of what we were interested in back in the days of writing the PDP volumes. Dave Rumelhart had written a paper called An Interactive Model of Reading. It was for a conference about reading, but it could be applied to language understanding, of course, but text comprehension. And his central message was that whenever we interpret anything, we have to use context. And in a popular book that I've been writing with a man from India named Gaurav Suri, we queried the latest GPT instance to see how well it was able to use context. So Gaurav presented this prompt: I use its bark to make paper. In the previous sentence, make your best guess about what the word it refers to. And ChatGPT said, in the given sentence, the word it most likely refers to the bark of a tree. And then he gave it another prompt: I use its bark to keep the house safe. In the previous sentence, make your best guess about what it refers to. And ChatGPT again gives a good answer. In the given sentence, the word it likely refers to a dog. The use of bark suggests a protective behavior associated with dogs, and they're commonly known for guarding homes by barking to alert their owners of potential threats. So this is what Sam Altman was talking about. It's answering questions for you, probably one you knew the answer to already, but doing a pretty good job of it and speaking to you in very nice English sentences as well. Okay, so LLMs are pretty good at language processing. I'm not claiming they're perfect at it, but I want to focus now on reasoning and problem solving. And we're going to ask the question, how good are they at this kind of process? So here's an example that of something I probed ChatGPT with not too long ago. I think probably about a little over a year ago now. I asked, can you place 1x in each row and column of a 4x4 grid without any of the x's being adjacent, horizontally, vertically, or diagonally? And GPT-4 said, yes, it is possible to place 1x in each row and column of a 4x4 grid without any of the x's being adjacent, horizontally, vertically, or diagonally. Here is one possible solution. Now, I think if you look at this, you might notice that this doesn't satisfy the conditions. Specifically, these two x's are adjacent diagonally. And I had previously asked the model if it understood what that meant, and it gave me a good answer. So the model gave an answer which wasn't entirely correct. And so I said, hey, it then went on to say this to sort of nail its kind of conclusion. In this arrangement, none of the x's are adjacent in any direction, meeting the specified conditions. However, I said to it, well, your grid seems to have diagonally adjacent x's in the second and third rows. Do you agree? And the model said, oh, apologies for my mistake. You are correct. My previous example does have diagonally adjacent x's in the second and third rows. Unfortunately, it's not possible to place x's in a 4x4 grid without any of them being adjacent horizontally, vertically, or diagonally. However, it turns out it was wrong again. And here I am showing you that indeed there is a solution where none of the x's are adjacent horizontally, vertically, or diagonally. So I ended my session with GPT-4 at that point. So these kinds of mistakes are extremely well known. They're often called hallucinations. And, the big AI companies are working very hard to improve reasoning in machines. We now have things like DeepSeek that are supposedly much, much better than GPT-4 used to be a year ago or so. And all of the different companies are putting out, machines that are getting better and better by various benchmarks all the time. But I want to just ask the questions about ourselves as well. Are we any smarter than these machines? By the way, I was introduced to somebody who was a leader of AI. I don't really consider myself to be an AI researcher. I'm still a cognitive scientist, and my ultimate goals are still to understand the human mind. And I find these models' behaviors, as I've already said, in some ways very satisfying and interesting, but also maybe they're telling me something that we can think about how to understand ourselves as well. So let's look at a couple cases of human reasoning. Here's a question for a game contestant. A Cadillac, or maybe a fancy new, very expensive car of some kind, is hidden behind one of three doors. Goats are hidden behind the other two doors. A contestant initially selects door. Oh, yes. The game show host is offering the contestants a chance to pick a door and maybe win the car. So the contestant initially selects door one, and the game show host then reveals that there's a goat behind door three and offers the contestant a chance to change his guess. Should the contestant keep his original guess or switch to door two? This is called the Monty Hall illusion. The correct answer is you'll increase your chance of winning from 1/3 to 2/3 if you switch. But most naive human participants choose to stay rather than switch. According to Wikipedia, when the puzzle and this correct answer were published in this woman Marilyn Savant's column in Parade magazine in 1990, approximately 10,000 readers, including nearly 1,000 with PhDs, wrote to the magazine, most of them calling Savant wrong. Even when given explanations, simulations, and formal mathematical proofs, many did not accept that switching is the best strategy. And according to the mathematical columnist Andrew Vasansky, when he mentioned this problem to his friend Paul Erdos, the famous mathematician, Erdos said, no, That is impossible. It should make no difference. So famous mathematicians can be fooled or can think that something is true when in fact it's not. Let me give a more straightforward example that's been the subject of very intense investigation by cognitive psychologists since the 1960s, even 50s even. So a man named Wason at the University College London first used this game to probe humans' logical reasoning. He presented his participants, who were university undergraduates at University College London, with cards like the one you see here, with the instruction that each card has a number on one side and a letter on the back. So some of the cards are face up and some of them are turned over so that you're looking at the back. And he asked which card or cards must be turned over to check if the cards all obey this rule. If a card has an even number on one side, then it has an X on the other side. So think for a minute about your answer to this question. Most human subjects in Wason's experiment turned over the 6, which is a good thing to do because if there was some letter other than an X on the other side, that would clearly violate the rule as stated. But very few participants turned over the other card that is actually relevant to the answer. The other card you have to turn over is the card with the Z on the back, because if it had an even number on the other side, then that would violate the rule. Instead, most subjects turn over the X, but it doesn't really matter what's on the other side of the X, right? The rule doesn't say that there can't be an X if the other side is something other than an even number. So people are not intrinsically logic machines. And Wason was extremely interested in this and did many subsequent experiments to try to understand better what was leading them astray. And among other things, he tested people who were PhD students or even professors in math and logic. And when they weren't cued to engage as logicians, they often made the same kind of mistake. But subsequently, researchers found that the content of the description of the puzzle made a big difference. So here's a variant of the very same task, which could be called a common sense reasoning task. The cover story is a little bit different. The cover story says, each check to the right is for a purchase at a store. Each check has an amount of a purchase on one side and a box for the manager's approval on the other side. Which check or checks must be turned over to check if they obey this rule? If a check is for more than $25, then the manager's approval box must be checked on the back. And of course, everybody turns over the check for $35 to see if the box has been checked. But many, many more people than in the standard logic game also turn over the check that does not have the manager's approval because if the check is for more than $25, then that's a problem. Somebody has passed a check without it being approved by the manager, and the amount is large enough that this could be a problem for the store if the check bounced. So when people are given essentially the very same sort of logical structure within a context where they have prior knowledge and experience, they tend to perform better. Characteristic. So this graph here comes from a paper that was led by two DeepMind researchers, one of them my former PhD student, Andrew Lampinen, and another one, Ishita Dasgupta from India. And in this study, they compared humans and language models on three different kinds of problems. Arbitrary, realistic, and nonsense problems. So we're not going to focus on the nonsense problems, but the arbitrary ones were like Wayson's original problems, and the realistic ones were like the example with the check and the manager's approval. And what they found was that in all of the different groups that they tested, including human subjects, but also several different language models, the models and the humans did much better with the realistic problems than with the arbitrary ones. In fact, the worst group was a subset of the humans who responded quickly to the question and sort of didn't spend a little time thinking and deliberating. The humans who were slower showed not a huge advantage for the realistic, but some. And this study was done online using Amazon Mechanical Turk. It's a cautionary note that human subjects on these online platforms are not necessarily engaging in deep thinking all the time. I think in Wayson's in many experiments that are done in a laboratory, for some reason, people are more likely to do better. Maybe they're also typically university students who are more likely to think carefully than others. But in any case, humans are far from perfect, and the average human, most of the humans were in this fast condition and did very, very poorly indeed. Experiment. The language models do better overall, but still, the key point is that they all show this advantage for a realistic scenario about which they have some experience based on the information, their training, the data they've been exposed to over the course of their lifetime. So it seems to me that humans and language models have a lot in common. We're not perfect thinkers, neither are our language models. We're good at using context in familiar situations, and the language models are too. But we're far from perfect reasoners in abstract reasoning situations. So here's an interim summary. Machines can hallucinate, but humans can too. Humans and machines can fail seemingly simple logic puzzles, but can seem smarter if these problems are posed with familiar scenarios. This invites the conclusion that we are not intrinsically the kinds of logic machines that some once claimed we are, and that our machines aren't intrinsically logic machines either. There's a kind of natural intelligence here in both ourselves and our machines, much like what we sought to capture in the PDP work in the 1980s. Okay, fine. But humans can go beyond their natural intelligence. We have these inspiring examples of humans like Newton and Darwin and Einstein and even Dave Rumelhart, who thought really long and hard about how to improve on the learning algorithms that neural network researchers had been using up to the time that we were working in the early 1980s, and developed, in Dave Rumelhart's case, the backpropagation learning algorithm by thinking carefully and systematically about a problem and working out a solution that, of course, backpropagation, which Rumelhart worked out, he wasn't the first to do it, but he did work it out, and he applied it to many examples and showed that problems that people didn't think neural networks were ever going to be able to learn could be learned using his simple learning rule. This was a feat of him exerting his natural intelligence to solve a problem that he wanted to solve. So, to me, this is the hallmark of our human intelligence. We can solve problems even if we're not perfect logical reasoning machines. And how about our machines? How are they doing in this? Well, I want to stress two ways in which we're still smarter than machines. So the first one is that today's language models are trained with up to 100,000 times more training data than a human could experience in a lifetime. Just to make this point sort of salient, I have depicted the relationship between the amount of data that, for example, DeepSeek was trained on in its pre-training. 15 trillion tokens of high quality English text. And the human upper bound for the number of words or tokens of text we might experience in a lifetime, it's been estimated to be something like 1.5 times 10 to the eighth tokens. I always have to remind myself how much that is. I think that's about 150 million tokens. You could correct me if I'm wrong. I'm one of those fallible human intelligences. But anyway, the ratio is stark. And there's a little tiny red dot down here. I don't know if you can even see it, that corresponds to the fraction of this entire blue space that would be the amount of data that a human could experience in their lifetime. Okay, so that's one incredible difference between humans and machines. It's a huge gap to bridge. Relatedly, machines can fail to generalize in seemingly obvious ways, while people sometimes generalize far more successfully. And I'm going to be illustrating that in the next few minutes here. So here is a striking result that was published in a paper in 2024 that revealed a phenomenon called the reversal curse, which is the finding that a language model could know the answer to a question when it was posed in one way, but it wouldn't know the answer when posed in a different way. So the researchers asked the model, "Who is Tom Cruise's mother?" And the model answered, "Tom Cruise's mother is Mary Lee Pfeiffer," which is correct. But when the researchers asked the model, "Who is Mary Lee Pfeiffer's son?" the model had no idea. It said that as of September 2021, there's no widely known information about a person named Mary Lee Pfeiffer having a notable son. So if you know that Tom Cruise's mother is Mary Lee Pfeiffer, it seems natural to think you'd also know that Mary Lee Pfeiffer's son is Tom Cruise, right? They went on to show that if they fine tune a model with a synthetic fact, and they used a range of different synthetic facts like these. For example, they trained it with Daphne Barrington as the director of A Journey Through Time. And if asked who is Daphne Barrington, the model would say the director of A Journey Through Time. But if they asked it who is the director of A Journey Through Time, the model would not have any idea, would behave exactly as poorly as a model that hadn't been trained with this at all. And similarly in the opposite direction. So this is a striking phenomenon indicating that the model is learning this information at least when it's fine-tuned, in a way that's very different from how it feels like we would learn this kind of thing. And if it's not maybe too surprising when you think about it. So I have this generic example here. John's father is. This is presented to the model, and the model is supposed to answer Bill. And we're imagining that the model is going to have to use the correct answer, Bill, to teach it how to use these input tokens to produce the answer, Bill. So we use the backpropagation algorithm that Dave Rumelhart developed, and we pass it backward through all of the connection weights in this column here, and it, because of the query-based attention at each of the levels of our transformer, it actually gets backpropagated backward through the network, and it allows the network to change even the way it encodes John and the previous tokens so as to make the model more likely to complete this sequence with Bill. Okay, so far so good. But why should that have any effect at all on answering the question, Bill's son is John? It's never predicted John. It's never predicted from Bill or the word son. So indeed, there's no transfer at all. So the models, we clearly are doing something very different from this when we're learning. So we'll think more about that over the next few minutes here. I'd like to tell you now about an experiment that my student, Andrew Nam, who's now a postdoc at Princeton University, and I did a few years ago, and in which Andrew found that humans can learn far faster and generalize far better than connection-based learning models do. So Andrew was fascinated by the puzzle Sudoku. He was actually quite an expert in it, and he still knows strategies that I can't even understand myself. But he studied a fairly simple Sudoku strategy. He took humans with no prior Sudoku experience and told them that the goal of the game is to start from a grid with some digits filled in and add digits so that each house, row, column, or 3x3 box contains exactly one instance of each digit. And then each human participant was shown a grid like this one, and they were walked through the reasoning that allows them to determine that one of the two candidate digits, and by that I mean the digits that are appearing 3 times outside of this highlighted house, this column here, must be the digit that goes in the green cell. So the basic idea of this strategy is that since each house must contain exactly one instance of each digit, if you can be sure that a given digit can't go in any of the other cells in the house, then you know it has to go in the target cell. So in this case, the target cell is the green cell. And the candidate digits here are 2 and 9. And if you consider one of them, let's say the 9, and you ask, well, could the 9 go in any of the other cells in this house? Well, it can't go here because there's already a 9 in this 3x3 box, and it can't go here because there's already a 9 in this row, but it could go there because there isn't any 9 in the same row, column, or box as that cell. So we can't be sure that the 9 should go there. But on the other hand, the other candidate can't go in any of these, can't go here, and can't go there, and therefore it must go here. So our tutorial explained this to the subjects, and then they were given 25 more problems with the same target cell, the same target house, in this case a column, but it might have been a row. Different participants had different rows or columns and different cells within the rows or columns. And also they only a subset of the digits could possibly be the target digits. It was 4 out of the 9 digits that could be were used as the possible candidates that could be the answer that should go in the target cell. And about 1/3 of participants, who we called solvers, got the idea after a few trials. So here's a display of the results. After the tutorial itself, a few subjects had probably already gotten it, but the overall error rate was still about 50%. By about the third trial, almost all of these people who eventually solved it were only choosing between the two candidates, or what we call prevalent digits that occurred in the context. That's what these red bars mean. They chose the wrong candidate, so those are still errors. But by the time you were about 10 trials in, these subjects were only occasionally choosing. This is over the group of solvers. Were only choosing between the two candidates and only making mistakes less than 10% of the time. So it took at most about 10 trials to get it, if they were going to get it. Now, not everybody got it. The remaining participants mostly got stuck just guessing randomly between the two candidate digits, or using a strategy like, oh, if the digits in the target house were mostly odd, I guess that the answer had to be even, and that has no chance of being correct greater than 50% of the time on average. So that was not a successful strategy. So although not everybody learns it, when the solvers, what they learned generalized nearly perfectly from this very, very narrow experience. So during practice, the target cell and target house are held constant, and only 4 of the digits can ever occur as candidates. Like in this example, there's only 2 of them shown here. Maybe the 4 and the 6 were the other 2 candidates for the target digits. And the test phase includes trials in which the house type, so whether you could be switched from a row to a column, or the cell within the house, or the digits that are being used, could all be switched. And basically the finding was that the effect of changing the candidate digit set was absolutely tiny and statistically insignificant. the effect of switching from rows to columns had an effect for the first block of trials. The first few times subjects saw it, but very quickly, this is the average over the first 8 trials. This is the average over the second 8 trials. The effect went away. So they had adapted to this switch very fast. Of course, the non-solvers continued to fail in the test phase that we ran after the training phase. So what happens if you teach a neural network this problem? Well, Andrew tried using a recurrent relational network that it had achieved state-of-the-art performance when trained to solve very hard Sudoku problems. This was a proud achievement of Google DeepMind some years ago now. But when he trained it with examples from the same restricted data distribution, it required hundreds of times more training samples and completely failed to generalize to held out digits. So just like the reversal curse, the model was overfitting to the training data. And yeah, so that's very similar to what happens in that case. So I don't think humans are really learning by gradient updates at all in these kinds of settings. I think we're learning in a very different way. We're learning in a way that connects with some sense of a understanding of why what we're doing makes sense. And this is something that I'm still trying to fully understand, but it appears that it's connected with the ability to use an explanation to help you guide your thinking. So our tutorial presented the hidden signal task, first explaining the basic principle, then walking participants through an explanation of how to determine whether a candidate digit could go in the target cell. And we also provided explanatory feedback when participants made mistakes. So we told them, for example, that if they chose the 9, that the 9 could go in one of the other cells, and so you couldn't be sure that it had to be the digit that should go in the target cell. And so our basic belief here is that humans were sort of constructing for themselves their own way of understanding this based on what we said to them and the feedback that they got and their own thinking about the problem. And we find correlational evidence in support of this theory. At the end of the experiment, we showed them one more grid. We asked them to say which digit went in the target cell, and then we asked them to explain the strategy they used so that someone else could use it to solve the same puzzle. And most solvers actually gave explanations of their problem-solving strategy, and that we could diagnose which of several variants of a valid explanation they were giving from this. And it was even true that the solvers that gave clearer explanations performed a little bit better. This probably wasn't statistically significant, but it was pointing towards that idea that the ones that had the clearest mental picture of this that they could explain performed better during the generalization phase of the experiment than the ones who were a little bit vaguer in their explanations. So furthermore, in a follow-up study that we haven't yet published, only about 10% of participants solved a simpler version of the hidden signal puzzle when they were only given accuracy feedback. They didn't figure out the solution at all in the number of trials that we gave them, even with a simpler version of this task. So I also want to point out that explanation-based learning was studied in the 1970s by AI researchers and cognitive scientists. And it was proposed as a very important feature of the way we learn. But it was hard to implement in the AI models of the day because these models didn't really sort of understand very well, of course. But this is a fundamental limitation. Models trained to predict tokens or to maximize rewards are not benefiting from explanation-based learning. And I raised this point with a couple of OpenAI researchers who gave a presentation at Stanford's Human-Centered AI Institute a few months ago. And they said, I asked them if anybody had ever tried to get models to learn from explanations. And they looked at each other. They said, well, that's an open research question. So I want to give you an example of two participants' explanation. First, the solver. This is what the solver said. He said, I located the larger square with two numbers in it, the 2 and the 9, that also contained 3 small blue squares. This told me the green square would have a 2 or a 9. In fact, all the puzzles had this structure. They always had both candidates in one of the boxes that was in the target house passed through that, and both digits were in that box. I then checked to see if 2 could fit in one of the 2 remaining blue squares. Since there was already a 2 in each row, I knew 2 had to be the solution to the green square. This guy really understood it, right? And he explained it in a way that you can use. Here's the non-solver. I went through a process of elimination by checking which numbers were already included in each square, since you can't duplicate numbers. But to be honest, I'm not sure if the 2 should go in the first, third, or fourth blue box, or if the 9 is in the second, third, or fourth. Sadly, these puzzles had made me feel not very bright. So, the ability to think clearly and exploit explanations and follow them systematically to execute a procedure is, in my view, a very central aspect of our human cognitive abilities. And it's one that separates those who are going to turn out to be able to be systematic thinkers like Einstein or Newton or Rumelhart, And I don't think our models have quite gotten there yet. I think there's a lot left for us to learn about how we are able to organize our behavior in this way and how we're able to achieve amazing scientific breakthroughs as well. I realize I'm almost out of time, and I do have one more little point I wanted to share. I'm going to assume I can use another 5 minutes, if that's okay. So let me just say that unlike fine-tuning, models do not exhibit the reversal curse when their given information is available in the context window. So here's the same example I showed you before. John's father is Bill. The model is presented with this information. It is essentially presented in context, and then it's given Bill's son is, and they're actually quite good, even relatively medium-sized language models, not the You don't even need to test a huge one for this to work out. So the model is able to use information in context. Presumably, when it gets to the word is here, it's issuing a query. Is there anybody out there who could be Bill's son? And somehow or other, the model has represented that information in ways we're not fully sure about yet in the context so as to be able to answer that question. So that's impressive and exciting, and I think a big source of inspiration and excitement for further research. But because I'm running low on time and I've already sort of belabored my point here, I'm going to very briefly say that the use of information in context is an amazingly powerful feature that these models are able to exploit to some degree. They are much better able at doing it than humans. So if you tell humans a few facts that they have to reason with, and you've just told them this, and they're supposed to hold them onto them in their memory, they get confused very quickly. But if they're given multiple repetitions, they may do something that models don't do, which is that they may organize this information into a structured way that allows them to abstract and support inferences. So in this study, which is going to appear this year in the Proceedings of the Cognitive Science Society, my student Jerome tested models where, after learning to answer true sentences like Kennedy is better at chess than Einstein and Roosevelt is worse at chess than Einstein, were probed to answer inference questions like true or false, Kennedy is better at chess than Roosevelt. And to make a long story short, we tested them on their generalization to transitive inference questions like, is Kennedy better at chess than Lincoln, for example? And this is what this was the next slide. Somehow I hit the wrong button there. If you present the set of facts in context, with just one presentation of these facts in the context, the models are not quite perfect, but with two copies of the set of facts in context, the models can correctly retrieve all of the answers to all the questions directly given. Humans are much slower to learn this stuff if given them, and they have to memorize them using their fallible human learning system. But they will gradually get better and better at them over the course of about 20 repetitions of this set of facts in this experiment, whereas models trained with fine-tuning are much slower, require many more repetitions to learn. And interestingly, the models are perfect at this point, or virtually perfect, with very occasional mistakes, with the items that they've learned compared to the humans. The humans are still making mistakes, even some mistakes, even on the learned items, but the humans are not affected by reversals, whereas the models, the fine-tuning models, are completely at chance with reversals. The chain of models which use in-context learning with the chain of thought are actually doing much better with reversals. The models also are able to do some of the inference problems. So if they learn A is better than B and D is better than E, everybody does pretty well with A is better than E. That's a result there. But I think the most interesting thing is that humans come in two types. Some humans, in the course of seeing these items over and over again to answer these true false questions, organize the material in their mind into a linear chain. And if you ask them afterwards, did you figure out that there was a ranked list of these items? They say yes, and they could tell you what it is correctly. And these humans generalize very, very well at test time. They show, they're very fast to answer all the questions as though they're all sort of equally consistent with the facts that they have. And but the models don't do that spontaneously. If you give the GPT model the ranked list in its context, it will behave the same way as the humans who did this spontaneously, but the model doesn't do it spontaneously. Okay, so that's the point I wanted to make. So here are my takeaways. When you train neural networks by fine-tuning their connection weights, they learn slowly and generalize very narrowly. In-context learning may be a small step forward, but it is far from a perfect solution. Humans can sometimes learn very quickly from instructions and explanations, forming useful abstractions and organizations of content that supports generalization. And my conjecture is that successful human learners are goal-directed learners who seek ways to structure their own understanding. They can make mistakes and go down blind alleys, but with persistence and self-criticism, they can achieve breakthroughs of the kind that we associate with Newton, Darwin, and Einstein. And capturing these human abilities is a challenge that AI has yet to address. Okay, thank you for listening, and sorry for going over a little bit.